Hey guys, Andy Robertson here at CQE Academy, and I'm really excited for today's video where what I'm going to do is I'm going to walk you through 10 questions from the statistics portion of the body of knowledge. We're going to go through one question from each of the 8 chapters within statistics. I'm going to explain how to solve the problem, how to recognize what type of problem it is you're solving, how to look up the right equations that you need to use on the exam, and then obviously walk you through the process of working those equations and solving the problems. And in the process of doing that, I want to share a free resource with you. I call this my free cheat sheet. You can get it at cqeacademy.com/free cheat sheet. And what I've done is I've taken all of the equations in the CQE Body of Knowledge for statistics. There's 165 equations. I've taken all those and I've condensed them down into a single 10-page PDF that you can use to help prepare for the exam, and then obviously you can use it on exam day to save you time. A lot of people waste time flipping through their book, looking up equations, and maybe they don't find the right one because there's different equations. I want to give you this free resource so that you're as prepared as possible and you understand how to use the equations and you're ready on exam day. All right, the second free resource, stick around to the end where I share another link to another free resource where I'm going to give you a bunch more practice exams to help you prepare for the CQE exam. All right, let's head over to the computer and get started.
All right, let's get into this. Okay, so what I wanted to do is I wanted to make sure that as we talk about statistics, we cover the entire CQE Body of Knowledge. So if you go over to the Body of Knowledge, which I'll link below in the description, there's 8 sections. You can see them all here. And I wanted to do 10 questions. So I decided to do 2 questions from statistical decision making because that's a really big chapter, as well as statistical process control because that's another big one. And then as we go through this, I don't just want to talk about how to work the equations, but I want to teach you how to know what equations you need to use. Because the first step in solving any problem is asking yourself, okay, what type of problem is this? And then once you understand the problem that you've been given, it's all about learning how to work the problem. The other thing is I'm going to add timestamps here to all the different questions. If you're good with standard deviation and you're good with probability and you're good with the normal distribution, you can jump right into statistical decision making and you can see ANOVA or linear regression. And that way you can kind of pick and choose which ones you watch. All right, let's get into it. Okay, so the first one, this is very basic, right? We're here in collecting and summarizing data. And on the CQ exam, you're almost guaranteed to get a question like standard deviation or variance. So here's the question. Calculate the sample variance for the following data set. Now again, the first step in solving any problem is identifying what type of problem it is. And again, if you want to get this free cheat sheet that I'm about to reference, go to cqeacademy.com/free cheat sheet because here's what it looks like. On the cheat sheet, you're going to find in the very top section is going to be all about collecting and summarizing data. And what you see here is there's 4 different potential equations that you might have to use to calculate either sample standard deviation or sample variance or the population variance or the population standard deviation. Now, given that the question actually says the word sample variance, we know that this is the right equation to use. So we're solving for S squared. Here's that equation, and I want to show you how to calculate this. In real life, obviously, we have Excel, we have Minitab, but on the CQ exam, you're going to need to know how to calculate this by hand. And it all starts by calculating X bar. We know what our X values are, right? 3, 5, 7, 9, and 11. But to actually do this calculation, the first thing we have to do is to calculate the sample mean value. And that's basically the summation of our values, 3, 5, 7, 9, and 11, which sum up to 35, and then we divide by n. And in this situation, we have 5 data points, so n is equal to 5, and our sample mean is equal to 7. Now that we have the sample mean, we can start putting together a table to do the calculations. So the way this table works is I've got all my individual x values, and now what I want to do is I want to compare that x value against the sample mean. So this should be the sample mean. I don't know why it always gets cut off like that. But essentially what I'm doing is I'm comparing every individual value against the sample mean. So 3 minus 7 is negative 4, 5 minus 7 is negative 2, 7 minus 7 is 0, and so on and so forth. And then the next step in the operation is to square it. So before we take the sum, we're going to square it. So if we take these values, negative 4 squared is 16, 2 squared is 4, and so on and so forth, we can basically sum up these squared values. So if we do that, the sum of these differences squared is equal to 40. And now we can basically plug that back into the equation to start calculating the sample variance. So again, we have 40, and we're dividing by n minus 1, so that's 5 minus 1. And our sample variance is 40 divided by 4, which is equal to 10. If you got 8.0, that means you likely calculated the population variance and you forgot to So divide by n minus 1, you just divided by n, which is 5. So 40 divided by 5 is 8. And then if you took the square root of your calculation, you calculated the standard deviation, which are these two answers. So 10 here is the right answer. All right, let's move on to the next one. Okay, so you're preparing for an upcoming production run where the likelihood of a defect A, let's say we've got 2 defects, so the likelihood of defect A is known to be 7%, and the likelihood of defect B is equal to 4%, and there's an overlapping 2% of the population that has both defect A and defect B. All right, so both of these defects can be reworked simultaneously. What is the total percentage of product that should be planned to be reworked? Again, right, the first step in any problem is understanding what type of problem we're trying to solve. And when we talk about probability, right, we can go again to our cheat sheet and we can talk about, is this an OR equation or an AND equation? And because we're trying to find the total percentage of defective products, it's going to be an OR situation because we're going to have to rework a product if it has defect A or defect B, or if it has both. So let's talk a little bit about how to calculate that probability. So when we're calculating the union of 2 events that are not mutually exclusive, the way we calculate that is the probability of A plus the probability of B minus the intersection of A and B. So we know that A has a probability of 7%, B has a probability of 4, and that 2% of the population has both A and B. All right, so we can basically plug in what we know and calculate the answer to be 9%. We take 7 plus 4 minus 2 is 9%. Now, I want to graphically show you what this looks like because this might be a little bit confusing. So this is a picture that I like to use that represents the union of 2 events that are not mutually exclusive. So over here on the left, we have event A or defect A, and that's 7%. And on the right here, we have defect B. And like the problem statement said, is that there's an intersection between these 2 events where 2% of our population has both defect A and defect B. And the probability that we're trying to calculate it can be visually thought of as like this area here shaded in blue. And when we calculate that area, we take A plus B minus the intersection because essentially when there's an intersection, we don't want to double count those defects. So 9% of our total product produced will have either defect A or defect B. All right, probability. So a shipping operation distributes product or ships product at a mean time of 48 hours from the receipt of an order. They get an order, 48 hours later, they ship it out, right? Maybe that's your standard Amazon 2-day delivery. And there's a standard deviation of approximately 6 hours shipping. What percentage of shipments go out between 42 and 54 hours? Now, we can answer this question, but I want to help you visually understand and visualize what's going on here in the problem. Imagine a normal distribution here with a mean of 48 hours and a standard deviation of 6. What the question is asking is, what is the area under the curve from 42 hours to 54 hours? And you can see what that looks like here. I've shaded that in green visually so you can see what part of the distribution represents that period of time. And the way we calculate probability using the normal distribution is with something called the Z transformation. So again, if you go to your exam day cheat sheet, you can find this Z transformation here to help you calculate the cumulative probability of the normal distribution. So let's do some transforming. So the first transformation is we're going to transform 42 hours, which is this data point X, into a Z score. So 42 minus 48, that's our mean value, divided by 6 is a Z-score of -1. So essentially, we've transformed this X value of 42 hours into a Z-score of -1. We can do the same thing with an X value of 54 hours. We can transform that into a Z-score. So 54 minus 48 is 6, divided by 6 is +1. And of course, you can see that over here, right? We transformed this X value into a Z-score. And now that we have these Z-scores, we can translate this into a probability score. This is a normal probability table. And the way this thing works is you start here on the vertical axis. This is the actual Z value, the ones place and the tens place. And then across the top is the hundreds place. And essentially what we're looking for is the intersection of Z of 1.00, which happens to be 0.34. Now let me show you what this looks like graphically. So the way this table works is that number that you saw, that 0.34, represents the area under the distribution from the mean value to our Z-score. So from the mean to z equals -1 is 34.13%. And then on the right side, from our mean value to our +1 z-score is another 34%. And cumulatively, if we go from z equals -1 to z equals +1, we're capturing 68% of the distribution, which is the answer to the question. 68% of our shipments go out from 42 hours to 54 hours from the time of receipt. That's how you solve a probability equation using the normal distribution. All right, let's keep going. So statistical decision making. I honestly feel like it's kind of cheating a little bit to give you the type of question, right? Remember, when you're on the CQE exam or if you're in real life, you're going to be given a problem statement and you don't know what type of problem it is. So remember, the first step in solving the problem is reading the problem, understanding the context clues and the variables that you've been given, and translating that into what type of problem it is that you need to solve. So let's go through this and let's look at what we know. We sample 60 units, okay, and we're measuring the width of the product, and the sample mean value is 6.75, so we know X bar. And we also know the population standard deviation is known, and it's 0.75 inches. We also know that our sample size is 60 units, so we've sampled 60 units, and we know we want to calculate the 95% confidence interval. So here it's pretty easy, right? The question tells you what type of question it is. We want to know the confidence interval, the 95% confidence interval. So we have all of our variables here. So again, we can use that free cheat sheet to look up the right equation associated with a confidence interval. And remember, we're looking to calculate a confidence interval for the population mean. We know our sample mean of 6.75, and we're trying to create an interval estimate of the population mean. So when we go here to our exam day guide, there's actually two different equations that you can use to create a confidence interval for the population mean. And it all depends on what you know. So there's this column over here called use when. So for example, we use this equation here when the population variance is known, which we do know, and the sample size is greater than 30. So let's take this equation, X bar plus or minus a z-score times the standard deviation divided by the square root of n, and let's plug in our variables now and calculate the confidence interval. So we know the sample mean 6.75, and then the z-score. So this is the only piece of information that we don't yet have. And essentially what we have to do is we have to translate this alpha risk into a z-score. Now, instead of doing that for you here and showing you all that, what I'm going to refer you back to is a whole different YouTube video that I created on confidence intervals to show you the math behind why this equation is what it is and understanding the sample mean distribution and these critical z-scores. I'll link that in the description below, but go check that out. The alpha risk of 5% translates into a z-score of 1.96, and we can calculate our interval estimate to be 6.75 plus or minus, that should be a minus there, 0.189. All right, so let's keep going here in statistical decision making, and let's talk about an ANOVA table. So we have a one-way ANOVA analysis, and we have 10 treatment groups and a total degrees of freedom of 19. What we have to do now, the problem statement is calculate the F value for this ANOVA table. Let me show you how to do that. Now, before we get into the actual math, I want to again go back to our cheat sheet here and talk about how you can use the cheat sheet to answer these questions. So the first thing is, let's start with the end in mind. The F value is calculated as the mean square of the treatment divided by the mean square of the error. So we're going to have to calculate these two things. And the way we calculate the mean square is to divide the sum of squares by the degrees of freedom. So we'll do that for both the treatment and the error. And of course, to do that, we're going to have to calculate our degrees of freedom for the treatment and the total degrees of freedom. And we're going to have to calculate the sum of the squares. So let me walk you through now how to do that. Okay, so the first things first is the treatment sum of squares. So we need to calculate the sum of squares of the treatment, and we can do that using this equation here. So the total sum of squares is equal to the sum of squares of the treatment plus the sum of squares of the error. We know that the total sum of squares is equal to 100, that's right here, and that's also equal to the sum of squares of the treatment plus 55, which is the sum of square of the error. And that translates to 45. We know the sum of squares of treatment is equal to 45. 45 plus 55 equals 100. We can do the same thing for the degrees of freedom. The problem statement tells us that we have 10 treatment groups. So what is the degrees of freedom of the treatment? Well, that's equal to A minus 1, where A is the number of treatment groups. So we've got 10 minus 1, and the degrees of freedom of the treatment is equal to 9. And now that we have that information, we can calculate the degrees of freedom of the error. We know that in total, the total degrees of freedom is equal to the degrees of freedom of the error plus the degrees of freedom of the treatment. So we know that 19 is equal to the degrees of freedom of the error plus 9. We can essentially rearrange this equation and calculate the degrees of freedom of the error to be 10. And now we're ready to calculate the mean squares. So the mean square of the treatment here is the sum of squares of the treatment divided by the degrees of freedom of the treatment. So we take our sum of squares, 45, divide by 9, which is our degrees of freedom, and we know that our mean square of the treatment is equal to 5.0. We can do the same thing for the mean square of the error. We can take the sum of squares of the error, 55, divide by the degrees of freedom of the error of 10, and get a mean square of the error of 5.5. And now that we have those two pieces of information, we can finally calculate our F statistic, which is simply just the ratio of these two variances, mean square of the treatment divided by the mean square of the error, and that comes out to an F statistic or an F value of 0.909, giving us the right answer. Now, the next step, if you're a quality engineer or a green belt or black belt, is to take this F statistic, compare it against a critical F value, and then make a conclusion regarding this ANOVA table and this analysis to determine whether we can reject the null hypothesis or fail to reject it. All right, let's keep going here. Now we're talking about relationships between variables. So let's say we've got a problem on the CQE exam or the green belt exam, and we've created a linear regression model, and our data has the following values. So SYY is 31, SXY is 12, and SXX is equal to 76. This is your standard linear regression problem. And the question is, what percentage of the variation in Y can be explained by the variation in X? And again, I feel like it's cheating because at the top of these slides, I'm putting relationship between variables. But even as you read the problem and you see words like linear regression or you see parameters like XYY and SXY, those should be the things that tip you off as to, okay, this is a linear regression equation, and I need to go to my exam day cheat sheet and I need to look at my correlation coefficient or linear regression equations. So if we go to the cheat sheet, there's two types of parameters. There's the Pearson correlation coefficient and the coefficient of determination. And if we read these and we're familiar with them, right, we know that the coefficient of determination, or R squared, reflects the percentage or the proportion of the total variation in Y that can be explained by the variation in X. So obviously to calculate R squared, we have to calculate R. So we can calculate R, we have SXY divided by the square root of XXX times the square root of SYY. And we can plug in our variables here, 31, 12, and 76, and calculate an R value of 0.25. Now, all we have to do to calculate our coefficient of determination is to simply square that. So 0.25 squared is equal to 0.06. And basically the conclusion is that 6% of the variation in Y can be explained by the variation in X. And to obviously to help you visualize that, I want to show you this picture. These are some common scatter plots and their associated R values. So for example, this one's pretty close to ours. And you can see that there is some low positive correlation, right? As X increases, Y tends to increase as well. But not much of that variation can be explained only by X, right? There's got to be some other independent factor out there that is causing some variation in our response. All right, SPC, let's get into this. Okay, so you're manufacturing some widget, and you're using an X bar and R chart to control a critical feature on the product. And you've measured, you know your grand mean, your X double bar, you know R bar, and you know your subgroup sample size of 8. Identify or calculate the upper control limit for X bar. Okay, so again, let's go back to our exam day cheat sheet. We've got a whole section on SPC. This is the X bar and R chart. And really the equation that we have to complete here is the upper control limit for X bar is equal to X double bar plus A2 times R bar. Now, the only thing we don't have, or the only thing we don't know, is the A2 factor. So again, on the CQE exam, you're going to have to look up this A2 factor, and you can use your exam day cheat sheet. So we know our subgroup sample size of 8, and we can simply get our A2 factor of 0.373. Okay, so I've added that up here to our known variables, and then I've repeated that equation, And let's start filling in what we know. 225 plus that A2 factor times 12 is an upper control limit of 229.48. All right, let's keep going. So let's stay here in SPC, but obviously let's move on to the attribute data control chart, or the P chart. So let's read our statement. What is the upper control limit for a P chart when the average daily inspection quantity is 50 and the historical percentage of defective units is 0.05 or 5%? Again, right, we just want to start by saying, what type of problem is this? And it's pretty clear in the problem statement that this is a SPC question on the P chart. So we go to our exam day guide, we look up the P chart equations, we know what the upper control limit calculation is, and based on the problem statement, we know that N bar is the average daily inspection quantity, right? This is the average sample size. That's 50 units per day. And on average, the average number of defects that we experience is 0.05 or 5%. And we can essentially plug those two variables back into this equation and solve for that upper control limit. So it's about 14%. Now I want to share something specific about the P chart. If you look at this chart here, obviously you can see the percentage, right? The percentage of defective items trending daily. But you'll also notice that the upper and lower control limits can change. So in this particular problem, we used N bar, which is the average number of daily units inspected. But your daily number of units inspected can change from subgroup to subgroup. Maybe on this particular day, we inspect 100 units or 200 units or 30 units. You can calculate a unique control limit using that N value as opposed to the N bar value, or the average daily units inspected. All right, let's keep going into process capability. This is section 7 in the body of knowledge. So again, the parameters and the problem statement are fairly obvious here. Calculate CPK using the following parameters. So we have an upper spec limit, a lower spec, a population standard deviation, and a population mean. Now again, to help you answer this question, or to help you understand process capability, I really want you to be able to visualize it. So here's that exam day guide. We understand the equation we need to use. Let's kind of throw that up on the screen. And basically we can start plugging in the values. So the upper spec is 205 minus the mean of 190 divided by 3 times S. Now in this particular equation, we have S, which is the sample standard deviation. In this particular example, we know the population standard deviation. It's really all the same, so plug that in here as the variation on the bottom. And then we can calculate the lower side. So 190 minus 145 divided by 3 times our sigma value of 10. And then basically we're looking for the minimum value between upper and lower. And if we keep running this out, we can calculate our process capability to be 0.5, which quite frankly is not that good. And I want to help you visualize this and again, just kind of understand process capability more deeply. So here's our distribution. We have a mean value of 190 and a standard deviation of 10. And if we overlay our specification limits, you can see that we're not centered between the spec limits. And basically what that means is everything in green here is going to be conforming to the specification, and then everything in red here is going to be out of spec. And that correlates with our CPK value because we're going to produce a lot of non-conforming products. And you can see here on the lower side of the distribution, that should say lower spec, we're 4.5 standard deviations away from the lower spec. And on the right side, we're only 1.5 standard deviations away, which again explains that CPK value because we're pretty close to the mean here. Now, if we were to shift our distribution, if we could center up our process around a mean value of 175, we'd be 3 standard deviations away on both sides, and our CPK value would go from 0.5 to 1.0. All right, let's keep going. Last but certainly not least, design of experiments. So here's the question. You've performed a full factorial DOE to improve the yield of a process. So the response here is yield, and we have 2 factors at 2 levels. We've got a high and a low for factor A and factor B, and we've measured the following responses. You can see here that as we go from high to low and we vary our different factors, you can see that our yield is changing. And we have 4 treatment groups. Now, how do we calculate or how do we estimate the effect associated with factor B? Again, we can go to our exam day guide. We can find the DOE portion of that exam day guide. And we can find this equation down here. So this is how we estimate the effect of any particular factor in an experiment. So let's see what this looks like in real life. So here's that equation. We want the average at the highs minus the average at the lows. So what does that mean? How do we do that? So for factor B specifically, the first two treatments have factor B at a high. And so what we do is we take the average value of 64 and 75, and then we have to take the difference of that against the average at the lows. So for example, for factor B, where we have lows in treatment groups 3 and 4, and those have yields of 87 and 95. And then if we just kind of play this out, what we find is that as we vary factor B from high to low, our yield actually improves by 21.5% from high to low, right? So that's the estimated effect of factor B, which is pretty substantial for yields to change by 20%. That is a big deal. All right, that was it. Again, I wanted to wrap up with those 2 free giveaways. So if you're preparing for the CQE exam, go sign up and get this free guide, this free cheat sheet. It has all 165 equations from the statistics section of the body of knowledge. And that way, when you take the exam, you are as prepared as possible. You have the best resources, and you're going to manage your time wisely because you have a very condensed version of this cheat sheet to really help you be successful. And then free practice exams. I'm a huge believer in practice exams. Go to cqeacademy.com/free practice exams to get more of those. I've got statistics practice exams. I've got all sorts of other free practice exams that you can get for free. And again, start practicing and getting ready for the exam. All right, that was it. I hope you enjoyed it. I've got a bunch of links in the description below. If you really loved this and you thought it was valuable, hit that like button. That way I know to continue creating content just like this. And if you want to stay on this journey to become a CQE and pass that exam, hit that subscribe button and that bell icon so that as I publish new content, you get notified and you keep learning and growing and pass the exam. All right, thanks so much. Bye.